basically this change of variable formula but for the volume integrals. We did the change of variable formula, but for double integrals we would like to do the change of variable formula for the volume integral. But for the change in variable formula, for example, in planes, okay, so we knew that we must have a diffeomorphism. Okay, we must have a diffeomorphism that takes me from one coordinates to another coordinates. Okay, so when you are solving the volume integrals, okay, quite often practically, your problem is kind of you'll find your problem mostly in rectangular coordinate, but it turns out that doing it in rectangular coordinates is nightmare. So you want to turn it into some other coordinates actually, like spherical coordinates or cylindrical polar coordinates or maybe some other coordinates. Okay. Sometimes you have coordinates. So if your picture is symmetric, maybe you can kind of estimate it with the sphere and use spherical coordinates or cylindrical coordinates. Or if your picture is nasty that you want to, for example, deal with, or the situation is nasty that you want to deal with, then you need to sometimes create your own coordinates actually, some curvilinear coordinates. But mostly we'll be dealing with here in this course with spherical coordinates and cylindrical polar coordinates actually. So last time I told you that you have two recipes to really reach this point actually. You can have many recipes to reach this point actually. Okay. By rectangular coordinates, I mean that I'm moving along x-axis, and along y-axis and along z-axis and reaching this point actually. Okay, maybe I reached this point. In rectangular coordinates, it has this coordinates a, b, c. So what does this mean? That this distance is a and this distance is b, and then I'm moving this distance above to reach it actually. Okay. So you can assume that if you want to, so if I treat all this as a plane and I want to reach this point, and I'm sitting in a bug is, for example, an ant is sitting in the corner of this, what do you call it, room, and it's only allowed to move along, say for example, horizontal, vertical, x, y, and z axis, then the bug is going to move some distance along x-axis and then some distance along z-axis and then to come at the top to reach, for example, this point. So that's a recipe. But that's really our imagination. This is not something reality. So I have a space and a point in it. So that's how I want to understand it. But the other way could be that, you take this same point, but you assume that this same point is a point on a sphere actually. This point is sitting on a sphere, okay, of the radius that is so it's like, what are the radius of this sphere? So whatever the distance between this point and the origin is in the rectangular coordinates. Okay. Then if you want to, for example, if a bug wants to reach to this point, okay, and it's only allowed to move this r, theta, and and it's only allowed to move on sphere, then he has to pull out some distance, okay, and reach on the surface of what you call sphere. So how much distance it needs to cover?
Which is the radius of the sphere, sir.
And then move an angle, longitudinal angle, okay, and move along, for example, longitudinally along the sphere. So this is equivalent to saying that you need to make an angle theta, for example, okay, and then need to move, in a latitude manner. So he has to take some latitude to reach this point actually, okay. And if you, for example, measure this angle, so this angle is what you call phi, okay. So I'm going to say that the coordinates of spherical polar coordinates are theta phi. Okay, so you need to pull out, move longitudinally, and then move in a latitude manner, and then reach this point. So the same point, the space is not changing. So previously you kind of had a fictitious cube through which you reach this point, and now you have a fictitious sphere through which you reach this point actually. And you can have a fictitious cylinder and a fictitious paraboloid, you know. So you assume this point to be anywhere actually. So you just have to reach this point using, you know, the geometry of, what do you call, the object that you are putting it on actually. Is it making sense? The question is, you know, if the both points are representing the same points, what is the relationship between both? Okay? And if you remember, we derived it actually. Okay? So we are not getting into all these details, but we derived it. That the A is going to be, okay, so what was A? Is going to be r cos theta cos phi. So we derived it in last class. You know, watch it again if you wish. And B is going to be, and it's better to call it x, y, z. X, y, z are the arbitrary point. Okay. I can call it x, y, z. And y is going to be, what do you call? This r sine theta cos phi, and z is, what do you call, r sine phi. Is it making sense? So that's how they are related with each other. So that's how, if you have been given an r theta phi, you can compute its position relative to rectangular coordinates. That how much this point is away, you know, how much you want to reach this point, how much you need to reach, you know, along x-axis, y-axis, and z-axis. Okay, if you know the r theta phi. But you can go other way around as well. So that's what we also discussed. That I mean, if you want to find this r, you need to square all x square plus y square plus z square and take a square root. That's going to give you, what do you call, r. Okay? And similarly, if you want to, for example, angle, say, theta, okay, so you want to find the angle theta, so just take the ratio of y with, what do you call, x, okay, and you know, you're going to get what? Tangent theta, r tangent theta equal to, x, y or x actually. And then from this you can deduce theta. And for the phi you can use, for example, this same equation. Are you getting the point? So you can interchange between them. Jay.
Should I turn on flaps?
Sure. Is it making sense to you? Okay. What would be the Jacobian of say x, y, z with respect to, for example, r theta phi? So what would be the Jacobian of x, y, z with respect to r theta phi? Okay? So you need to do what? You need to compute a matrix actually. And how does this matrix is going to be?
3 by 3.
So it's going to be 3 by 3 matrix. And what would be the first row of the matrix?
So first row is deal with
So differentiating x with respect to r and differentiating it's going to be, we need to compute also the determinant actually, so matrix and then determinant. So partial by
X by y.
and partial b by partial r and then partial x by partial theta and then partial y by partial theta and partial z by partial theta and then partial x by partial phi and partial z by y by partial phi and partial z by partial phi. Okay? And then I can compute also the determinant of, I know I have to know, so if I have been given all this stuff, you can easily compute this matrix.
in vertical, would it not be like that derivation of x with respect to r, y with respect to r, z with respect to r in first column, sir?
Achha, so you need to transpose.
Oh, yes, yes.
Okay. So just transpose. This would be the Jacobian. I was relying on you.
Yeah.
I'm bad at memorizing formulas. Okay, so I can compute the determinant of this, what do you call it? This r theta x, y, z by theta, for example, phi, and it turns out to be this quantity. So I need to compute the determinant of it. So I'm just writing it that it's going to be r cos squared phi. So r squared cos squared phi. So this would be the determinant of it. Is it making sense?
Yes.
Okay. Now here's the thing. So something that takes you from one coordinates to another system of coordinates, for example, in our planar case was what actually? So it was really the Jacobian, the diffeomorphism actually.
Yes.
So diffeomorphism was that map actually. So here you can also have a map phi, okay, that is going to be a map from, for example, R3 to R3, and maybe I define it as R theta phi. So if I have been given R theta phi, so I can compute x, y, z in rectangular coordinates, and it's going to be R cos theta, cos phi, R sin theta, cos phi, and R sin phi. Okay. I mean, if you remember, if you keep this in, like if you remember, you also had almost a similar parameterization of, what do you call, sphere.
Yes.
So from where that parameterization came, so it comes from the same analysis, precisely same analysis, that okay, I have been given this, what you call u and v, which are really the longitude and latitude, so you are fixing the radius. So if you have a sphere, so you are fixing the radius, okay, so it's not going to depend on r, okay, so all these expressions are not going to depend on r if the r is fixed. So they will be variating when theta and phi are variating actually. So this longitude and latitude is variating actually. So in other words, u and v. So when you may compare theta and phi with the u and v, with the when we are talking about sphere and its parameterization actually. So it's really the same formula. Okay. Question: is this phi a diffeomorphism? So what properties diffeomorphism should have?
Diffeomorphism has three properties. It should be 1 to 1, and the determinant should not be 0.
Okay, so one of the central thing that it can have is that the Jacobian of the phi, which is this guy,
Should not be.
it should not be 0, but this can be 0 if you allow phi to be anything, okay, anything, then it has it could be 0. So the Jacobian can vanish actually.
Yes.
Okay, Jacobian can vanish because you can have angles phi where the cos can be 0.
And also the other thing, the odd multiples of pi by 2 in
Yes.
cos.
Yes. If you take any odd multiple of pi by 2, so this will be 0. So in its current form, this phi is not diffeomorphism actually. So I want to turn it into a diffeomorphism. So what should I do? So the first thing, that if you want your diffeomorphism to be non-zero, you need to restrict your phi. Okay, so where should be my phi actually?
It should be set from 0 to 2 pi, but there is restriction that it should not include pi by 2.
It should not include.
Pi by 2.
So it's
Phi should
better
be odd multiple.
that you usually say that it should be between
Oh yes.
minus pi by 2 to pi by 2, and then
or 0 and
minus pi between, say for example, minus pi by 2 to 3 pi by 2, and so on and so forth, and excluding these all odd points. Okay, so phi should be here. It could be between minus pi by 2 to pi by 2, could be between pi by 2 to 3 pi by 2, excluding pi by 2 and 3 pi by 2, and so on and so forth. Positive, negative, both. So if your phi is here, you can have it. But still, there is a problem.
that's radius.
So what is the next thing that the phi must be actually? So it must be a bijection actually.
Yes.
So if you have a phi, okay, that is defined in this manner, so can it be bijection?
Yes, sir. On average,
There can be several points
that is repeated.
where it's repeated actually.
Yes.
Okay. So what should be done? So what would be the first, for example, such points where the values can be repeated? For example, if you have this sphere, if you remember, we did this analysis.
Yes.
We did this analysis. We said that, if you really want to turn, a sphere into a surface, you need to exclude some points from the, for example, domain actually.
Yes.
Okay, so what would be the points where, phi is going to repeat its values actually? So if you fix the r, for example, so what would be the thetas and phi's actually where it can repeat the value? So in other words, I'm starting, for example, from this point. Okay, so how much I should revolve around, for example, sphere, so that I repeat and reach on the same point actually.
2%.
So if you allow theta to be, for example, if you allow it to take the value 0 and 2 pi, okay, or maybe pi and 3 pi or whatever, are you getting the point? Then, you have a trouble. You have a trouble. Okay, you have a trouble. So what should be the restriction on the theta? So if you want to make it, for example, if you're only interested in the interval, if you want to revolve around the sphere once, not more than once actually. So what should be the restriction for the
So
sphere?
the revolution should be less than 0.
It should be between 0 to 2 pi. Okay. It shouldn't be 0 and 2 pi because it's going to start. But it could be, so it's not about only 0 and 2 pi, so it can be minus pi to pi as well. So any interval of the length, for example 2 pi, so in that the sign, like these symbols are going to repeat their, what do you call, these functions, sine and cos, are going to repeat their values. So you need to exclude the, what do you call, roughly endpoints.
Sir, if we include 0, then it will still work, isn't it, sir? Because we are not repeating the point.
That could be also a possibility that if you include one endpoint but not the other.
Yes.
This is also-
Any side, sir.
Yes. You get a good point. And you're going to have a similar restriction on the phi. So you can move, for example, in a longitudinal manner and you can reach to the same point, but you can also move in a latitude manner and roughly vertically and then reach to the same point actually. Okay, so it could be, the phi should be between 0 to 2 pi. But there is another restriction that phi should be here as well.
Yes.
So phi should be in the two intervals. So where both things are going to be true, both conditions are going to be t. In other words, the j phi is non-vanishing and so this condition requires that your phi should be here, minus pi by 2 to pi by 2. And one-oneness says that your pi should be, for example, here, 0 to 2 pi. So the question is, where both conditions will be valid, so it must be intersection.
Yes, sir.
Intersection actually. Okay. So what you're gonna say, what you're gonna take, for example, is going to be that you just consider their intersection actually. Are you getting the point? Okay. But I think this also has a length 2 pi, so we still will be safe actually. Isn't it? So minus pi by 2 से pi by 2 के दरम्यान क्या distance होगा? So
यहाँ पर
length pi है.
1
pi by 2. Yes, should be pi. So in other words, your phi is diffeomorphism. Your phi is diffeomorphism. So this whole analysis is kind of revealing, okay, is going to be diffeomorphism. If you choose your r, theta and phi from where? There is no restriction on r. So r could be anything, okay. So r could be, let's not treat it as 0, because if you have 0, you have nothing. Okay, but you are sitting at origin. Okay, and the theta should be between minus pi by 2 to pi by 2, and your phi should be between 0 to okay, 0 to 2 pi.
Sir, it means we are also restricting R because we are not allowing it to be 0. It means also we have the restriction on R.
Restriction on R is वजह से 0 है because then you don't have physically a sphere actually. Think about it. I mean, if the radius is 0, what do you mean by where you are actually? So you are at origin. So R equal to 0 is not interesting case actually. So you are talking about origin. So So the interesting case would be when R is
Non-zero.
so phi would be diffeomorphism here actually. Okay? Phi is going to be diffeomorphism roughly here. Is it making sense? And now phi, can be treated as what a good candidate map. If you make the change of the coordinates, okay, you are safe. Okay, you are safe. There is another way to look at it in this manner, that if you, for example, if you have a space actually, so you have some volume, okay, and you take a small chunk in that volume actually. You take the dV. Okay? So the dV in rectangular coordinates is going to be what? dx, dy and dz. While in spherical coordinates is going to be
dr d theta d phi.
dr, d theta, dz. But is it going to be the only thing that you should have?
For a spherical
You need to multiply it with the Jacobian actually. So the Jacobian, so what would be that? R cos square phi.
So will it not be dr d theta d phi, sir?
Oh yes,
Cylindrical coordinates.
yes. I get the point. So dV in rectangular coordinates is going to be this, and if you're turning yourself from rectangular coordinate to the what do you call polar coordinates, you need to multiply this. And what would be the interpretation of it actually? So what would be the interpretation of Jacobian actually? So somehow this cube is turning into really a sphere, a tiny sphere, okay? And their volumes are not exactly equal actually. Okay, but their volume is different. So in other words, if you're going to multiply this factor with the volume of a sphere, that's going to give you the volume of what do you call this small cube actually. Are you getting the point? Are you getting the point?
Yes.
It's making sense. So it's the same intuition as you have in the two dimensions. There you have the area, and now you have the volumes actually. Okay, so these are equal roughly. Okay, why they are equal? If you don't put this, then they are not equal, because you're talking about two different objects. So their volume can differ. But this is compensating actually, making sure that, okay, you are transforming things from, what do you call r theta phi to xyz, or xyz to r theta phi through a diffeomorphism. Okay, the diffeomorphism is not only going to map the points onto the points, but is going to map the chunk of volumes to a chunk of volumes actually. But how their volumes are related, okay, so they are related in this manner, multiplied by the Jacobian. Okay, so the Jacobian is really compensating for losing or missing the volume depending on the angle, what angle you take phi. So they are even. So I discussed this last time in detail, but I just added some more things in it. So I'd like to talk another, kind of coordinates. So you need to understand basic assay, the essence of it actually. That in spherical polar coordinates, you are assuming actually that there is a fictitious sphere, that contains your point actually. Okay, and you want to move on sphere. So we have three dimensions, ways to move on the, and you are sitting at the origin and you want to reach to some point onto the sphere. So you need to pull out the sphere and move, longitudinally and move with a certain angle latitude to reach that point. So these are the three motions that you require to reach at that point. And for example, if I write now cylindrical coordinates, so what do you mean by that? So you can guess it already. You're saying that, okay, I have the same points. Okay, I have the same point, and let's imagine this point lies on the cylinder actually. So it lies on the cylinder. So it really lies on a really fun. cylinder actually. And you want to reach to this point actually. So what are you going to do?
We will
You're going to pull out,
to the R with
make some angle,
and move
okay, theta,
and go up.
and then go vertically. I don't need to make angle actually, because that's really a vertical motion actually. So just make a vertical motion and reach here. So you need really three quantities. So R,
Theta is there.
what is the radius of what you call the base of the cylinder, or any part of the cylinder actually. Think about it. Wherever you go, you have the same radius actually. Okay. And then theta. Okay. So how much you need to turn so that you can be right in front of the point, and then you need to move above actually, which is okay. So this cylinder is fictitious. So it doesn't. So it's not something real. So it just exists in our head. Okay. And this allows you to do the manipulation. So instead of cylinder, you take something else. You take paraboloid instead of cylinder. Actually, you take a hemisphere instead of cylinder, and ask what would be the how the coordinates would be related with each other. Okay.
How to select theta? How to select the angle?
What do you mean by that?
I mean, on what we have to select the angle.
No, you have to just think about it. So do we have a cylinder? So we have some kind of cylinder with us, or some bottle, water bottle, something like
So
that.
Marcus,
So you can have a page and you can treat the so maybe this. So I have water. So let's assume this to be a cylinder. So that's really a cylinder. Okay, and think about it. You are, so it's like, maybe this is one. So it's right at the corner of it actually, but in such a way that the middle of the cylinder is really the origin of what do you call this XY plane. Okay, so what you need to do. So I want to reach this point on the cylinder. So what I need to do. So I'm gonna move horizontally, okay, and then make some angle, and then pull up to reach this point actually. So you need three quantities to specify any point on. Okay, so you need to make some. So you need to pull out, and then make some angle, and then come above to reach, for example, one of the point on the cylinder. So you need three quantities roughly. Okay. I mean, if R is fixed, then you need only two quantities actually. So what angle should I make? And then how above should I go actually? And then you ask the same question what you asked here. So so this has a description actually. Okay, rectangular coordinates. But these rectangular coordinates are how related with these coordinates. You can ask even more interesting question. You can say how these two coordinates are related with each other. So spherical and cylindrical coordinates. So if you have been given r theta phi, can you compute r theta z actually? You can already see that r and theta, r would be different. R would be different. You have to be careful when you are, but you can find a relationship. It's not a big deal. Okay? So you will learn, for example, in differential geometry some part where you're going to learn curvilinear coordinates. So if you're going to take a very abstract curvilinear coordinate, one coordinate, and you take a very abstract another coordinates, and what are the general formulas for converting one kind of coordinates into the other kind of coordinates. So you can always do it. Is it making sense? Okay, so let me redraw this a bit neatly, and let's try to find the vector. So I'm here, so I'm covering some distance r. Okay. Okay. And I need to, for example, make some angle. Okay. So that I can reach right in front of this point and then rise actually. Okay, so this angle will be theta. Question is how these r, theta, and z are related with x, y, and z. Here's an important thing. There is a distinction between r here and here. Here the r was the radius of the sphere actually. Okay. while here R is not the radius of the cylinder really, it's the radius of a section of a cylinder actually. So it's a circle that lies on. So if you cut it, somewhere, so this would be really the radius of the cylinder. So it's the radius of the circle actually, the base of it, or maybe wherever you want to cut it. This number would not change. So you're not going to say that it's the radius of the entire cylinder. So even if we say that it's the radius of cylinder, we mean